Welcome to This Explainer, where we're going to completely flip how you see the physical world. The reality you interact with every single day. The chair you're sitting on, the screen you're looking at right now, it's mostly an illusion. Today, we're uncovering exactly why the world feels so incredibly solid when, fundamentally, it really shouldn't. Let's kick off this scientific detective story with a pretty simple, almost childlike question. If you push your hand against a solid brick wall, why doesn't it just phase right through? We've all seen ghosts do it in movies, effortlessly gliding through barriers. But when we try it, we just end up stubbing our fingers. So, what's actually stopping you? To figure that out, we need to take a microscopic journey.
Part 1. The Empty Space Mystery.
To crack this case, we have to zoom way in to look at the atomic building blocks of literally everything. Picture a cute, squishy 3D atom on your screen. Right at the very center, you've got this tiny, densely packed core, the nucleus. And zooming around that nucleus in this frantic, buzzing cloud are the electrons. That right there is the fundamental structure of all matter. But here's where our story takes a huge twist.
Okay, get ready for a genuinely shocking truth. 99.9% of that atom, it's actually just empty space. The nucleus and the electrons only make up a tiny 0.1% of the whole thing. To put that into perspective, if the nucleus of an atom was the size of a little marble sitting right in the center of a massive sports stadium, the electrons would be like tiny gnats buzzing way up in the highest seats. Everything in between is absolutely nothing.
Part 2. The Electromagnetic Force Field.
Think about it for a second. If we're made of all this empty space, and the wall is made of empty space, it seems completely logical that we should just be able to pass right through each other, right? Two clouds of empty space should just seamlessly mix. But we are stopped dead in our tracks by our first major suspect, electromagnetic forces. This might completely blow your mind, but when you place your hand on a brick wall, your atoms are not physically making contact with the wall's atoms. On a microscopic level, you have literally never touched anything in your entire life.
So, if it isn't physical contact, what exactly is happening? Well, the electrons buzzing around the outside of the atoms in your hand carry a negative charge. And at the exact same time, the electrons buzzing around the atoms in the wall also carry a negative charge. As a fundamental rule of physics, like charges repel each other. They absolutely despise being near one another.
Imagine trying to push two cute, chunky 3D magnets together, but you have the exact same poles facing each other. As you squeeze them closer, you feel that invisible, squishy resistance pushing back, don't you? They just completely refuse to touch. That is exactly what's happening between your hand and the wall. The negative electrons in your hand are violently repelling the negative electrons in the wall. The physical sensation you interpret as hardness is literally just electromagnetic repulsion pushing back against you.
Part 3. The Ultimate Quantum Rule.
It turns out, electromagnetic repulsion isn't the only invisible bouncer at the club keeping you from walking through walls. There's another fundamental law of the universe at play here, called the Pauli exclusion principle. This is a massive, unbreakable rule in quantum physics, and it simply states that no two electrons can occupy the exact same space at the exact same time. It's kind of like having assigned seating in a movie theater. You just can't sit in the chair that someone else is already in. So even if we magically turned off that electromagnetic repulsion, this principle guarantees your atoms absolutely cannot overlap with the wall's atoms, making passing through basically impossible.
Part 4. Can we break the rules?
Now, you might be wondering, are there any loopholes we can exploit to bypass these strict quantum seating arrangements? Well, technically, yes. There's this bizarre phenomenon known as quantum tunneling, where particles can sometimes borrow energy and spontaneously tunnel through barriers they really shouldn't be able to cross. But before you get too excited about your new ghost powers, there's a pretty huge catch. While a single tiny bouncy 3D particle might pull off this disappearing act pretty regularly, humans are made of trillions of particles. For you to walk through a wall, every single one of your atoms would have to quantum tunnel at the exact same time in the exact same direction. The probability of a whole human pulling that off is so infinitesimally small, it's virtually zero. You could lean against a wall for the entire lifespan of the universe, and it still wouldn't happen.
Part 5. Case closed. The Illusion of Touch.
Let's put all the pieces of our atomic detective story together. Why do we stay solid, even though you, me, and everything around us is 99.9% empty space? There are 3 rock-solid reasons that guarantee physics will always keep us perfectly intact. First, the electromagnetic repulsion between our negatively charged outer electrons. Second, the Pauli exclusion principle, which strictly forbids our electrons from overlapping. And finally, the absolute limits of quantum physics at large scales, keeping crazy phenomena like quantum tunneling restricted to the microscopic world.
It really all comes down to this thought. Next time you touch a wall, or lean on a desk, or even high-five a friend, I want you to remember, you're not actually touching them. You are just hovering infinitesimally close, being violently stopped by incredibly powerful, invisible forces. I really hope this explainer leaves you looking at your own hands in wonder, because the reality of our physical world is far stranger, far more complex, and vastly more fascinating than the simple illusion of solidity. Knowing all this, what else in your everyday life do you think might